Water flows freely through the large tanks as shown. Determine the water depth HA. Now it seems like there's not enough information to solve what the water depth is, but let's take a look at it, and it's actually not as bad as it appears at first blush. This problem is going to require us to exploit some conservation of mass equations, but it's also going to require a couple of streamlines. So let's take a look at this. I'm going to pick out a couple of points, and then we're going to go about solving the equation from there. So the first thing I want to do is the surface of this tank I'm going to call point 1. Right at the exit of this tank I'm going to call point 2. Surface of this tank I will call point 3. And the exit here I will call point 4. Now as we look at this, we're going to be exploiting the concept of Bernoulli's equation. So let's first look at this and do our assumptions. Well, I'm going to assume that there's going to be a streamline. Now in this case, I've got two streamlines. Or actually, you could call it just one streamline, because the total pressure is going to be the same along there. So my streamline is going to connect point 1 to point 2 to point 3 to point 4. There is a line where the flow will connect those 4 points. And because Bernoulli's equation tells me total pressure at 1, 2, 3, 4, all going to have to be equal. I'm going to assume a steady flow. There's nothing in this that tells me it's time dependent. And actually this assumption is extremely important for this one, because if it was an unsteady flow, let's say that this tank was filling this one quicker than can exit, so it's like spilling over the sides, or the second tank is emptying quicker than the first one fills it, we wouldn't be able to solve this as easily as we're going to do. But since the fluid that's coming out here dropping into the tank is the same as what's coming out of here dropping into the tank, same as coming out of here dropping into the tank, we're going to be able to calculate out a solution. We're going to assume an inviscid flow, so we're not going to worry about the friction in here. And with water flowing freely, it's incompressible, so we can just make that assumption that it's incompressible. Okay, so where do we start? Well, I have some flow rate coming through, which is Q. So if I drew a control volume around this tank, well, Q coming in has to equal to Q coming out at 2. So now if I draw a control volume, the second one, around this tank, so what's coming in at 2 has to be coming out at 4. So conservation of mass tells me the volumetric flow rate at point 2 has to equal the volumetric flow rate at point 4. So the volumetric flow rate at point 4 is going to be what? It's going to be the velocity at 4 times the area at 4. Now I know what the area at 4 is. I don't know what the velocity at 4 is. But I do know there's a streamline that goes between point 3 and point 4. So let's write the equation for the streamline between 3 and 4. And what does that give me? It gives me pressure at 3 plus rho over 2 V3 squared plus gamma Z3 has to equal all of this at point 4. Rho over 2 V4 squared plus gamma at Z4. So what else do I know about this problem? Well, I know point 3 and point 4, the way I've got them picked, are both atmospheric pressure. Point 3 and point 4 are going to be equal to each other. I know point 3 is the surface of a large tank. That makes that 0, and that will end up falling out. So I'm going to take, if I make Z4 my 0 point, that falls out. And so what am I left with? Well, that's the equation. It will be the equation of a free jet. So if I go and I rearrange this, V4 is going to be equal to 2 times gravity times Z3. Take the square root of it. So now we just plug our numbers in. So 2 times 9.81 meters per second squared and I know that's 2 meters. And I take, oops, should be 1/2, not 2. So if I calculate that out, I can figure out that, okay, well, V4 is 6.26 meters per second. So now I know what the exit velocity is. So now that I know the exit velocity, I can sit there and I can calculate out what Q coming out is. Okay, well, Q4 is going to be velocity at 4, 6.26 meters per second, times the area at 4. So that's going to be pi over 4 times 0.05 meters squared. So that is my diameter. And so now if I calculate that out, 0.0123 cubic meters per second. So there is my flow rate coming out here at 4. Well, my flow rate at 4 has to equal my flow rate at 2. Conservation mass equation told me that. So what I can do now is I can sit there and go, okay, well, if Q4 is equal to Q2, well, that must mean that all of this stuff at Q4 is going to be equal to Q2, which is equal to V2A2. So now I can rearrange that equation and go, okay, well, Q4 divided by the area at 2 will give me the velocity at 2. So let's calculate that out, 0.123 cubic meters per second. I'm going to divide that by the area at 2. So I look at my geometry, pi over 4, 0.03 meters squared. And then when I plug that into my calculator, I will calculate out V2, which gives me a velocity of 17.41 meters per second. Now as I look at that, that's a much faster velocity than V4, but I have a much smaller diameter, which makes sense. It has to be going faster to get that fluid to come out. So let's move on to the next page here, just to give us some more room. And now what do I do? Well, remember I've got that streamline between 1 and 2 now. So now I'm going to write Bernoulli's equation between point 1 and point 2. So pressure 1 plus rho over 2 V1 squared plus gamma Z1 has to equal pressure at 2 rho over 2 V2 squared plus gamma Z2. I'm going to set Z2 to be 0. So that falls out because Z2 is 0. Pressure 1 and pressure 2 are both atmospheric pressure. They'll end up canceling out. V1 is the surface of a large tank. That will end up canceling out. And so once again, I'm just left with the equation of a free jet. So if I rearrange this, what do I have? I have V2 is going to be equal to 2G Z1, take the square root of. Of course, we already know V2, so we probably should have arranged that to be Z1, so let's do that instead. So I'm going to take Z1, and then I'm just going to divide through by the specific weight. Now, density divided by specific weight, since specific weight is just density times gravity, we're going to end up with 1 over 2g times v2 squared. So 1 over 2 times 9.81 meters per second squared, and then we're going to multiply that by 17.4041 meters per second, and we're going to square that. Meters per second squared, meters squared per second squared, that's going to leave us with meters, which is a unit of height, which is what I'm expecting. So if I bash those numbers out, I get 15.4 meters. So that first tank has to be 15.4 meters deep to keep the system running the way it is.